Okay, in the first part of this video, I'm going to review quiz 1. If you got less than an 8, you should watch this. And even people that got more than 8 might benefit from watching it. I'm going to try and keep it short. I'm going to emphasize some important points for all of you. So problem number 1, you were asked to do an estimate. And we've been practicing this. We want to have some idea before we begin what the answer is going to be. So if you consider a meter stick and you consider a gallon bottle, you should have guessed that it would take somewhere between 4 and 7 gallon bottles side by side or on top of each other to reach a meter. But then you have to realize that's just like 7 bottles. That's not a cubic meter. So a cubic meter, you would have 7 high, 7 wide, and 7 deep, or 6 high, 6 wide, and 6 deep. If you chose 6, you'd get 216. If you chose 5, you'd get 125. Those are all good estimates. This one, of course, is pretty darn close. Now, in part B, you got to do the problem. So what I'm expecting, what you must do is follow the course formatting. We have a special way of doing it, and this is what it would look like. 1 meter cubed, we're going to convert it. So the meters have to cancel, and we're going to have inches, so we're going to get cubic meters into inches, and then the gallons per cubic inches, the inches will cancel. So it should be written this way, and the units cancellation done. Now, an easy mistake, and many of you made it, was this is meters cubed. So what we know is 39.337 inches in 1 meter. So this whole thing has to be cubed. This number has to be cubed. The unit will get cubed. The 1 gets cubed, but that's 1. And the meters get cubed. So when we cube the meters, those will cancel. When we cube the inches units, those will cancel. But you must cube this number and then divide it by 231, and you would get this answer. But since the input, the 231 cubic inches, that's not an exact number. That's an estimate itself. And so what you had to do, and many of you failed to do it, was you had to report the answer as 264 gallons because it should only be 3 significant figures. So we're paying attention to significant figures, but the formatting really matters. Now what some of you did was you took a meter. This is fine. You can do it this way. You took a meter and you cubed it. So you cube the 1, you get 1. You cube the meters, you cube this number, and you get that there are 6,123, some decimal if you want to carry that, inches cubed in a meter cubed. Now, if you're going to use that, this is what you should have written. All right, so given this conversion done on the side, you just go to your 1 gallon, 231 cubic inches, and you multiply it by this. And I didn't mention it, but it's good to understand we're multiplying this by 1, right? We can multiply any number by 1. The units will change, but the value won't change. So 6,123 inches is equal to 1 meter cubed, so that's a 1. But conveniently, our inches cubed, not inches, but inches cubed cancel, and we're left with meters of 264 gallons per meter cubed. So this would be the formatting if you wanted to do it in 2 steps. Okay, now I'm going to move on to question 2, and then we'll move on to talking about quiz 2. And what I didn't mention in the beginning is I'll put a table of contents at the end of the video. Okay, question 2. This is directly from the lab, and it's always a good idea to review the lab. So last week we had 2 tasks. You should have studied them and reviewed them before the quiz. This week we had 4 tasks, and I'll talk about that in the next part. You want to review those 4 tasks, and you want to know if you try to remember what you did, just memorize it, it doesn't work so well. You want to know why. So in this case, go to the lab document, you'll see the details, but this figure captures what we did. We measured the height to our eye and give that a name. I'm calling it little h. You can call it X, Y, Z, A, B, C, but give it a symbolic name. Then the part that we needed to get from measuring the angle in this distance was this additional height above our eye. In the lab, I called that capital H. You can give it any name you want, but give it a name in the diagram. And in the diagram, put the symbols that you're choosing for each quantity and the number if it's given. Okay, so all this should be in the diagram, including the angle. I should have put the number in there, 40.2. Okay, now once we have this, we can see that the total height is going to be the sum of these. So we want to write that down, call it H pole, call it H total, give it a name. You can choose any name, but that name, in this case I didn't put it in the figure, but it's pretty obvious, the total height is the little h plus the big H. And the big H we get by doing trig. So this is opposite the angle, and we have the adjacent side. That's why we use the tangent of the angle, which is a number we have. So this is your generalized equation. This is your figure. That was part of the problems, to draw a good figure. Looking at the figure in the lab isn't good enough. You've got to draw these figures out with your hand before you get to the quiz. Otherwise, you're just going to flounder. And we always start with a generalized symbolic equation. We don't just jump into a forest of numbers. We want to show the reader and ourselves clearly how we're getting the total height. So this is something important to this course and that you need to practice. And you'll be part of every quiz and exam you take. Okay, once we have the generalized equation, then we put the numbers in. With the units, I ran out of space, so I didn't write tan 40.2 degrees here, but we put that in, and then we can just do the calculation. And we might write down extra digits, but our final answer has to be 3 significant figures because a lot of the data is only 3 significant figures. So this is what this answer should look like. Just getting the answer is at most half the problem. Being able to draw a good figure, being able to write the generalized equation, and following formatting that makes it easy for anyone to understand the problem is all part of the question. Okay, let's review for quiz 2. So first item, not on the screen, is vectors and scalars. Make sure that you understand that vectors are quantities that have a direction associated with them, such as displacement, velocity, acceleration, force, and momentum. Those are the 5 vectors that we'll see this semester. But anyway, there were other vectors like wind speed or something. So you understand the difference between vectors and scalars. Now, we're learning about motion. It's called kinematics. There's 2 sets of equations that should be understood and capture the concepts we're learning and tools for solving problems. So we learned 3 quantities: displacement, velocity, and acceleration. And we distinguished between average velocity and instantaneous velocity, and average acceleration and instantaneous acceleration. And those, the definitions of those 5 terms are found here. So, if you're asked to explain the difference between average and instantaneous velocity, you should start with these equations. Explain in words what each of them means, and then give an example to illustrate. Let's do that. Average velocity is this equation. You take, it's the displacement divided by the time. And the displacement, this is the definition of displacement. If I ask you to define displacement, you would choose this, and you'd say it's the change in position over the change, it's the change in position. So it's the final position minus the initial position. And since this is a vector, it can be positive or negative. So velocity, the average velocity of the change in position over time, you take the total displacement and divide it by the total time. That gives you an average velocity. And you might point out that that's different from average speed if the thing changes, if the object changes direction. To get the instantaneous velocity, when the if the velocity is constant, right? If it's 10 centimeters a second the whole time, it's the instantaneous is 10. But if the velocity is changing, you take the displacement over the time, but it has to be over a short time interval. That's why in lab, in task 2, when we wanted to measure the final velocity at the end of the track, we had to use the photogate, the ticker timer, or the motion sensor that could measure a very small distance in a very small time. If the delta x and delta t aren't close to 0, this is an approximation. So the exact result, the actual true definition of instantaneous velocity is the derivative of x with respect to t. These are the same thing. This is a way of defining the derivative. And so you should understand that. Now, an example, a cart going down a track. Its velocity is constantly changing. It starts at 0. It ends at some final large number. The average velocity is going to be an average that is not equal to any of those velocities except at one instant. So an example, well, I'm not going to take the time to go an example, but you could go 1 meter in 2 seconds and calculate the average velocity. We'll come back to that when we talk about task 1 and task 2 in the lab. And the instantaneous, the acceleration is just a change in velocity over time. And so for the average, it's very similar, the final minus the initial over the change in time. Since on a flat track, in most of the things we're studying, the acceleration is constant, there's no difference between these two. But when would the acceleration not be constant? Oh, if you were on a curved track, right? And we do see that a little bit in the MOPS. Now, the limit as delta t goes to 0 of that ratio of velocity to time becomes the derivative dv dt. But since v is already a derivative, you have Calc 1, if you've gotten there yet, the second derivative of the position vector with respect to time. So you should be able to say that about these. And this equation can be used to solve problems, but and so can this one. But for the most part, these are a definition of terms. Displacement, average velocity, instantaneous velocity, average acceleration, and instantaneous acceleration. And in physics, equations are often definitions of terms. So this equation we'll never use for calculation. We only use it to define instantaneous velocity. Now, if we take this, when the acceleration is constant, and rewrite it, we get this equation. And if we also recognize, like in lab, the average velocity is the final plus the initial divided by 2. And so rewriting this equation, delta x equals v average times t, we get this. And from these two equations, we derive these. And these are working equations. These are the equations that we'll use to solve problems. And so we'll often say, oh, use equation number 3 because the initial velocity is 0 and you can solve for acceleration. Or use equation 4 because you know the acceleration and the displacement, but you don't know the time. Okay, so that's the equation. A common question that I could ask is distinguish between average and instantaneous velocity. I just told you how to answer that. And on limited time on the quiz, you would write these equations down, you would say a few words, and you would give the example of a cart goes 1 meter down a track. Its average velocity is 1 meter down a track for 2 seconds, say, and its average velocity is 50 centimeters per second. So its final velocity would be double that, 100 centimeters per second. And then we can use this equation to calculate the acceleration. 100 minus 0 over 2 seconds would give us 50 centimeters per second squared. That would be an example to illustrate that you understand clearly the difference between average and instantaneous velocity. Okay, that's a lot of talking, but we don't have lectures, so it's important, in summary, equations are not just tools for calculations. If anything, that's, in my mind, the least, well, it's an important function. But they are ways of defining physical quantities that are precise. They are statements of relationships between quantities, such as initial, final velocity, and acceleration. And they are tools for calculating. So an essay question in physics should almost always involve using an equation and an explanation of the equation. So before any quiz, you want to review the equations of the week. You want to make sure you know what each symbol means, but you want to be able to make sure you understand the relationships and distinctions such as this between average and instantaneous velocity. So now let's talk about Lab 2. So the first item was equations and concepts, and now review Lab 2. So what did we do? Do you know what we did? We calculated, you were given an angle, and you calculated the acceleration using 4 different methods. So you should know that. And then you should review the 4 methods and know, given the data, how to do the calculation and understand how we got the acceleration from each method. Now, in every case except method 3, the initial velocity, well, in method 1 and method 2, the initial velocity was 0. Here we used a ticker timer and a motion sensor that did all the work for us, basically. So what we need is a time and a final velocity to get the acceleration. So how did we get the time and the final velocity in method 1? And how did we get the time and the final velocity in method 2? See if you can answer those questions. Pause the video, try to answer those questions, and then come back and I'll tell you what you should be remembering. And you can look at the lab, but on the quiz you got to remember. And remembering is easy if you understand, right? Okay, don't just watch. Make sure you've answered the question first. So method 1 is pretty straightforward. We measured a distance, a meter, and we used a stopwatch to get the time, and we calculated the average velocity. Then knowing that the average velocity is the sum of the initial and the final divided by 2, since the initial 0, the final velocity is double the average. And once we have the final velocity, then we just subtract 0 and divide by that stopwatch total time that took to go from a velocity of 0 to the final velocity, and thus we got the acceleration. And you can put numbers in there, like it took 4 seconds to go 100 centimeters. That's an average of 25 centimeters per second. And when you double it, you get 50. And then when you get 50 minus 0 divided by the 4 seconds, you're going to get 12.5 centimeters per second squared, because we did it in centimeters. Okay, method 2, did you do that yet? If not, pause and do that. Okay, method 2, in order to get the final velocity, we used a photo gate. So we measured, right? We measured a small distance in a small time, as close to 0 as we could practically do. So we used a flag that blocked the photo gate as it went through the end, and so you might have collected the data 2.5 centimeters. It took 0.05 seconds. That would give us a final velocity of 50 centimeters per second, and then it would be 50 minus 0 divided by the time. What's the time? This time, not the photo gate time. What's this time? This is the time we got with the stopwatch. Back here it was 4 seconds. What would it be here? It was the time between the top gate and the bottom gate, the time between the gates. And what you should have done when you did the lab is checked, was your stopwatch time the same as the time between the gates? Because it should have been. Well, the photo gates will be more accurate than your stopwatch time. So say we got 4 seconds again. This would be 50 divided by 4, and we would get an acceleration of 12.8. Okay, method 3, we used a ticker tape to show us the position. It's like an oil drop pattern, right? Or a motion diagram is also what we call it. The ticker tape gives us the position of the cart every 1/10 of a second. So here's a tape. Calculate the acceleration from this set of dots. Go ahead, pause the video and find the acceleration of this cart given these measurements in centimeters. Okay, pause. Okay, I fudged these numbers so they're pretty much perfect. So we can't measure this interval because these dots are bunched together. So the first interval we got was 5, then the next one was 15, then 25, then 35. This may not be to scale. So to do this problem as quickly as possible, I get the initial velocity. It's not going to be 0. It's going to be 5 divided by 1/10 of a second. 1/10 of a second is short, so we can consider this an instantaneous velocity, approximately. So that's my initial, and then I jump ahead to the last interval, and I get 35 centimeters in 1/10 of a second, right? So that's 350 centimeters per second. I ran out of space. Now we go up here, and the final is 350. The initial is 50, so that's going to be a difference of 300 divided by what? 1, 2, 3/10 of a second. So 300 divided by 0.3 is going to give us 1,000. Oops, I made the numbers too big. Anyway, that's what it would be for this. It would be 1,000 centimeters per second, which would be 10 meters per second. This would be like an object being dropped way too fast. So in hindsight, I should have made this 0.5, 1.5, 2.5, and 3.5 centimeters, and then it would have been 100 centimeters per second, which would have been more reasonable. Okay, method 4. What can you say about method 4? Okay, I won't ask you this, but just quickly, the motion sensor sends out a pulse which bounces off the cart and comes back. And it measures the time it takes to go and come back. And from the time, the position right is the velocity times the time. And it knows the velocity of the ultrasound pulse, so it gets the position. And then say 1/10 of a second later or some interval later, it calculates the new position. And so it gets a set of data, just like we did, of position versus time. And it collects it, and it uses that data to calculate velocity versus time. And so we ask the software to use the data it collects to graph the velocity versus time graph for the cart going down the track. And since the slope of velocity versus time is the acceleration, change of velocity over change in time, we can get the acceleration by getting the slope, and the thing might have not been perfect, but then you take a slope tool and you lay in a straight line that matches the graph the best possible, and so the slope, which is the change in y over the change in x, is the acceleration. And so we used a graph of velocity versus time in the slope tool to get the acceleration in method 4. That's it. Well, not quite. There will be a mock question, and I will pick something that lines up. I hope you saw there's a new KG mop video, and it's about 39 minutes. So if you watch from here to the end, it'll be 14 minutes or so of video, plus this is about 25 minutes. So the two videos together are about the time of one lecture. So go through those. You'll see what they are when you get there. Just review this, and I will give you some question that lines up with those MOP exercises, but it will be formatted in a way like I do in the video. Okay, that's it.